Right. So for those of you who like mathematics, I brought the paper. It's really 2 pages long. So after the talk, you can take a look. So I will talk about accretion, and to have a plan, let's have it by names. Bondi, about spellings. This spelling.
Let's see.
This spelling. No C exactly, because he was a Russian, right? The crazy spelling says that he's from Russia. And then Yasin, and then Vlasov. So accretion itself is the following problem. Suppose you have a gravitating mass, let's say a black hole, surrounded by some gas. And in astrophysics, for obvious reasons, we want to know how this gas will fall, let's say, for concreteness, onto this black hole. In particular, I will be interested in at what rate will this gas fall onto the black hole. Like, given conditions for the gas at infinity, let's say specified by density and sound speed, at what rate will it fall onto this black hole? In principle, another condition which I must specify is the velocity of the black hole, because usually the black hole will be moving through gas. And so I will be interested really in wind accretion. And again, my main interest is to calculate the rate of mass accretion. The previous time, or before that, we had this interesting discussion. Like, I think Sergey asked, would not the spin of the black hole influence the rate of accretion? Apparently not, because it appears that the fate of the gas is set at large distances. Near the black hole, the structure of the accretion disk or accretion whatever will depend on the spin of the black hole. But whether or not a certain amount of gas is falling onto the black hole apparently is determined only by these conditions at infinity, not by the properties of, which is counterintuitive, I agree. But also another point is that mostly when people talk about accretion, you must have heard a lot about accretion disks, whatever, mostly people are interested in the following problem. Given the rate of mass accretion, you set up some disk near the black hole with a given rate of mass accretion, and then you ask what will be the properties of radiation, stuff like that. But I will be interested in this. So that's what I will do. This
gas for you is just gas. It's not plasma.
We will talk about it. This why those names. So the Bondi part of the talk will be pure, if you wish, mathematical physics. Namely, I will show that for the adiabatic index equal to 5/3. So here I will be assuming stationary hydrodynamics, no magnetic fields. I will show that for the adiabatic index equal to 5/3, for a subsonic flow, the rate of mass accretion is given actually by what is known as spherical Bondi. Bondi knew this result for V equal to 0. This little paper demonstrates that it is valid for any V less than Cs. That is to say, no matter at what subsonic velocity the wind is blowing past the black hole will accept the mass at this rate given by the spherical Bondi formula.
And the number really is pi? I've never believed that.
Yeah, I will derive it in
Okay,
some
good.
sense, but you can look at the paper
That's
for.
And Andrei,
Yeah.
incidentally, that the fate is decided by the boundary condition at infinity, that an independent of spin. That's not true for a neutron star, right? With magnetic.
Yeah. There, of course, it will spit out a lot of gas. Maybe it's not quite true even for the black hole, because we will get to reality. Reality is always very different from this mathematical theories, right? Because in reality, a short answer that in reality, We will never know. I will get to this. Right, so you are saying, but even the black hole, because when the black hole spins, almost certainly it changes the radiative properties of this thing, okay? And if you release different amount of heat near the black hole, it is not unthinkable that it will influence the rate at which you accept the mass.
Yeah.
So none of the statements, when moved to the real world, is safe.
So for instance, yeah, I'm not aware with this most of this last name, but why there is no Eddington last name?
Right, for example, Eddington would be a good, exactly, right. But I have to talk about only a small piece of reality. Now, Schwartzman says Bondi doesn't work. He was the first to say it. By the way, another reason to discuss this thing, we have been informed that the Event Horizon Telescope will soon show us what happens near Sagittarius A star, and it will almost certainly confirm that it's not a Bondi law. We already know from different lines of argument that this is not Bondi, but this Event Horizon Telescope data release almost certainly will confirm.
Could you put the years?
Huh?
Could you put the year of these different things? It'll be interesting.
Bondi is 1950 something. That thing is my paper 2022. They, like they said, string theory is a piece of 22nd century physics which fell into the hands of 20th. So this is a piece of 19th century physics which fell into my hands. Schwartzman is of more than 1980. He was a very interesting guy. Typical Russian story. Apparently, he was a good pupil of Zeldovich, but he was not from Moscow. And in Russia, if you are not from Moscow, you couldn't do science because you have to whatever. So Sergei would understand, you would not. But anyway, so
I'm from Moscow, so I don't.
That's why you're here.
now the question is, if Bondi does not work, how can I have a right to even talk about it? That's why the name of Yesin is here. So Bondi does not work in real world. But for example, primordial black holes, if they are surrounded by this really unperturbed, right, almost uniform, perfect gas, there maybe Bondi does work. Maybe not, I don't know, this remains to be seen, but at least Yesin is an excuse for me to prove mathematical theorems, even if I don't know for sure that it does not work in real world today. But maybe it worked before, we don't know really. Besides, we will never know, so something which we can compute with confidence is already good. So Yesin names is here because that's why I can do both.
That's you see.
But also,
You see the C. That's how you see it.
yes, that one.
That's C.
It should have a C, not an
It's
S.
not an S. It's C.
Really?
Yes.
Yep. How many papers have you written so far, Gruzinov?
I wonder how I spell it in my acknowledgement. Nothing to be done. Right, so I discussed, because of Yesin's interest in this accretion thing, I have been discussing accretion with him, and then by accident, this little thing. Okay, so let's start with Bondi. So this is mathematics, and this should be doable. Well, I should stop at 1:30 or not?
Yeah,
1:30. Okay. So let's start with Bondi. So this is pure math. Namely, I will assume static hydro. That is to say, there is this black hole of mass m. Let me start with Bondi with zero velocity of gas at infinity. At infinity, I have gas of this density and this sound speed. and I will be assuming gamma 5/3, but from time to time I will put it as gamma, you will forgive me.
And gamma doesn't end up in your answer, right?
No, because the answer is only valid for gamma 5/3.
Ah.
This crazy thing that the accretion rate does not depend on wind velocity is only valid for gamma equals to 5/3.
Oh,
Which
and I
happens
don't
to
believe
which
it.
happens to be the adiabatic index of the interstellar medium of contrast model.
But only approximately. I mean, it's not exactly.
Yeah. Nothing is exact.
Right.
In real life, of course. But let's talk mathematics first, then we can descend to real life. So let's just do an estimate here. To do the estimate of the rate of, so given m, rho, and cs, I want m dot. First of all, of course, since I have 1, 2, 3 numbers, this dimensionful number can be computed by analysis of dimensions. But it's better to just understand it, namely define Bondi radius as a distance from the black hole at which the free fall velocity becomes of order speed of sound. Now, what is the significance of this radius? At this radius, random motions of the molecules get, so to speak, overwhelmed by the free fall velocity, and the gas has no choice but to fall onto the black hole, right? And then, of course, m dot will be of the order of Bondi radius squared cs times rho. Because by this time, rho did not change too much, the free fall is of order cs, so with cs we go through this radius, and if you plug in our Bondi here as gm squared over cs to the 4, cs rho, you will recover this formula, okay? So as an estimate, it's simple. But how Bondi managed to put a coefficient here is an interesting little calculation. Well, not little. In my paper, I call it a pearl of theoretical astrophysics, and I do think so. It's a highly non-trivial calculation. So it's static hydro, but let me write it as time-dependent hydro first. So my density is described by the continuity equation. Then I have early equation for the rate of change of my velocity. Under the influence of the gravitational force. And then I will assume, which will be true for my subsonic accretion, that there are no shocks, right? And if there are no shocks, then my gas will follow an adiabatic. And so my pressure, because you understand, to solve this, I need to express pressure in terms of rho. Normally, I would add some equation for the temperature, pressure will be rho times T, whatever. But since there will be no shocks, my gas will remain adiabatic. And so pressure will be given just by this formula, which means constant entropy, you understand, right? Entropy will be P over rho over gamma, where this constant K is, of course, fully specified by density and sound speed at infinity. Okay? So this is what we are solving. I can immediately specify for the stationary spherical flow, right? Again, Bondi, no velocity at infinity, the flow will be spherical.
And it's adiabatic because you're assuming, what's the assumption, that it's fast or that there's no radiation?
No, there are no
Because
really
there's no
assumptions, right? Because the only assumption is that it is assumed to be constant entropy at infinity, right? This assumption is where I specify by rho and cs. Once your entropy is constant at infinity,
Then you have to adapt to the
now
entropy.
this is, of course, if there are shocks, then shocks can lead to an entropy jump. But that's why I can do it only in subsonic region.
Sure, Andrei, so going back to the question I was asking, so if there is no dependence on the spin, for instance, is it because it's assuming that there is spherical symmetry and black hole doesn't
Here,
get,
here, of course, there is no dependence of the spin because there is no black hole, right? There is only a point Newtonian mass, right? We are computing spherically symmetrical thing,
yeah.
flow. So formally, if you want to see what will happen with the black hole, then of course it will not be spherically symmetrical to begin with, right? So, however, as far as I know, if you keep doing it in pure hydro, this wouldn't change much because at large distances it will start free falling like so. Then near the black hole you will perhaps introduce some asymmetry, but this would not expel the gas to infinity. At least this is common, how to say it, standard way of thinking. Besides RG, gravitational radius, where your spin will matter, happens to be 1,000,000 times smaller than Bondi radius, where the fate of the gas is settled according to Bondi.
This is really the accretion across the Bondi radius that you're computing.
I'm computing accretion at all radius.
You are, but if
it
you
will only
computed it at
work.
Bondi, you'd
No,
be fine.
look, another way to answer it. It will only work in the Newtonian regime. However, Newtonian regime extends 1,000,000 orders of 6 orders of magnitude beyond the Bondi radius. So very likely your black hole will be incapable of doing anything. Okay, so I specify to the, and I will use equals even though I mean equals up to a constant. Right? Through this area with this velocity, I get this much mass. Here, where I have used the adiabatic, and my constants are 1 whenever I wish. Okay? Now, this is all terms here are full derivatives. Come on. Gamma minus 1, which in my case is 2/3. Right? Right? Integrated. Plus some constant.
You're dropping dimensions, quantities.
I am dropping
Good,
everything.
fine, yeah, got it.
V squared rho 2/3 1 over r by 1, because at infinity my velocity is 0, density is 1, so at infinity I have to put this coefficient 1. Wonderful. Now let me do the following little trick here. Here I can replace velocity with rho. Squared multiplied by r. Okay? See what I have done? This is the beautiful calculation of Bondi. This is where it happens, where you take this equation and you multiply it on r. There is no explanation, of course, because that's why it's a pearl of theoretical astrophysics, right? So you multiply it on r, and then you notice that the same r cubed rho squared enters both of these terms. And here comes the argument by Bondi. Oh, I can move it up. Let me play one little dirty trick here. Instead of this 1 over r, I will use Paczynski Viter potential to account for perfect suction of the black hole. You will see why I need this device. Actually, in my calculation, if you wish. Okay? minus 0, where 0 is a positive number. It's like Feynman's epsilon, right?
That's allowed.
What?
That's allowed.
Okay, so now let us look at what this equation says. So before thinking, we can say, okay, you have solved it. Take an arbitrary m dot, then this equation will allow you to calculate rho at a given r, and you are done. So for different m dots, you can have various accretion flows. This, however, is obviously incorrect, right? There must be a unique m dot, right? If I set it up on my computer, the guess will end up going at some. In fact, when I was young and full of whatever power, I did not believe the Bondi argument so much that I did check it on a computer. I really did a time-dependent spherically symmetrical simulation to make sure that the rate of mass accretion is unique, right? Because here, what's the problem? Different flows are possible, but physically, of course, if you set it up on a computer, since what do you call it? Because of determinism, there will be a unique m dot, of course, right? So how can we get unique m dot from this thing? Here is how. Let us plot the left-hand side. Believe it or not, my extension of Bondi will be an immediate consequence of this, so we are not wasting time doing it carefully. Besides, it's very interesting. Okay, so let's plot the left-hand side as a function of this quantity, r cubed rho squared. R cubed rho squared at large distance, for large values of this quantity, it goes as this thing to the power 1/3. And if m dot was 0, it would have been this, right? Now let me choose some m dot. If I choose a certain value of m dot, that at small things I will be dominated by this exploding thing.
Sorry, what is on the vertical axis for you?
Just the value
The
of the left-hand side.
Ah, okay.
So left-hand side versus this thing. Thank you, by the way. That's exactly how you denote it in the paper, left-hand side. So it goes like this, and then like this, for a certain m dot. If I make m dot smaller, it will do this. If I make m dot larger, it will do this. Okay? So this is my left-hand side. What about the right-hand side? The right-hand side is easy, right? If it would have been 1 plus r. However, because of this plus 0, it is actually this. Right? At finite, at 0, it goes all the way to, okay? Now here, I don't have any free parameters, right? This is just
to minus infinity.
because if r approaches plus 0, rg, right? Replace it by rg, r over r minus rg. At r equals rg, this is equal to infinity.
It's not equal to
Right, and rg I just put plus 0, right? That's so this is now so the right hand side is set. Now question, what is a possible value of m dot? You see, we immediately see that large m dot is impossible. Remember, this is large m dot. I will not be able to be here, right? What is the meaning of this equation? For any given r, this gives me rho, right? If there is some flow onto the black hole, then at any r, I should be able to calculate rho. But if my m dot is such that this is my curve, then in this range of r's, I have no inflow. Wonderful. Too much m dot is excluded. What about too small m dot? If m dot is very small, then we should see what's happening. As I move here, right? So this is very small m dot, then I should do this. Suppose my m dot is like this. Then, as I move, boom, boom, I will have to move, boom, boom. which means that my branch at small radii happens to be exactly the same as it is at large radii. But this is nonsense, because this would correspond to 0 velocity near the black hole. This is totally unphysical. As a result, the only possibility is to choose m dot in such a way that these two minima coincide, and as I move here, I move here. Right? Because it can be shown that on physical grounds, this term should actually dominate near the black hole. The other branch is simply unphysical. This is the power of Bondi argument.
Did Bondi actually state it like that in the paper?
Yes, more or less. Okay, and then, like I said, this argument seems to be too smart for theoretical astrophysics, right? We usually just solve things numerically, whatever. But it can be checked, it works. This miracle does work. This is indeed the right rate of spherical accretion rate. Now,
And he did have to put RG in there?
no,
you
because
do
he
have to
no,
choose.
because he was doing it for gamma arbitrary,
I see.
and if gamma is slightly less than 5/3, this happens automatically. Since
I
I'm
see.
doing 5/3, I have to use this device.
Got it.
Okay, so what about my result here for different velocity? Well, it's really very simple. What happens to this is just, of course, you recognize this as Bernoulli equation, right? This is V squared, P over rho, enthalpy, potential constant, right? This is Bernoulli constant, gravitational, enthalpy, and velocity. So what will happen to this equation if my flow becomes aspherical? So in the presence of the wind, so now at infinity I have velocity, rho, and cs. So there will be some axisymmetric flow. As a result, my velocity will get components. If you really want to understand the group, just take one of those. It's only 2 pages. So this is what will happen to my Bernoulli equation. Now, the trick of the proof is as follows. Given this Bernoulli equation, let me try to follow, what do you call it? Bondi's. Let me try to mimic Bondi. What was the trick that Bondi did? He replaced velocity by the accretion rate. But now, of course, since my flow is not spherically symmetrical, my accretion rate is no longer just a function of radius, it becomes also a function of theta. Then, with a little bit of whatever, this becomes dm dot d theta, more precisely dm dot d omega. And this becomes whatever it is. Right, you understand why this becomes dm dot d omega, because at different, for any radius, the local rate at which you go in is given by the radial velocity and the density, right? So instead of having m dots here, I will have here dm dot d omega squared. What about this term? Since I want to get to physics too, I have to really, okay, but 10 minutes I can give it. What about this term here? You see, another important trick here is to realize that not only is my flow is entropic, it is also potential if I don't have any shocks. Potential means that my velocity can be written as a gradient of some scalar function. Okay, it is a potential flow. Why? Because the flow at infinity is potential, obviously. Right? If I define scalar potential as the scalar product V times R, then its gradient will be equal to V. So constant velocity is a potential flow. The force which acts here is potential. If I am at constant entropy, this force is also right? This is just a gradient of the enthalpy. Pure gradient, pure gradient. If this is pure gradient, then you can show that this product is also a pure gradient. This is a well-known result in hydrodynamics. That's the reason why many flows are potential, because many forces are potential, and then a flow in a potential force is entropic. Without shocks, which produce entropy, will be potential. Now, why do I care so much that my flow is potential? Here is why. Let's consider my flow near the black hole. Very close to the black hole, to leading order, my velocity will be of order r2 minus 1/2. This is a self-consistent assumption, okay? So let me explain again. I will try to, this is another reason when Yasin was helpful, because he was doing similar things. I will try to expand my flow near the black hole in inverse powers of r, right? Then the leading order term will be r2 minus 1/2, just the Keplerian velocity. But since my flow is potential, it means that my psi goes as r2 1/2 near the origin. If my psi goes as r2 1/2 near the origin, then obviously my density, which means that psi is to leading order in R is this. Analogously, density to leading order in R should be this. Why? Because their product should be divergenceless, and then this dictates these powers, right? Because divergence RV is 0, right? And so constant m dot, right? So if V is like this, just from here, if V is r2 minus 1/2, then rho is r2 minus 3/2 at small r. But then my continuity equation actually tells me that psi of theta is constant. Okay? But again, if you like mathematics, take a look. So it can be shown actually that since psi of, so near the, just by asymptotic analysis, I know that near the black hole, the flow becomes very spherically symmetrical. If it becomes, which means that my potential is a function of, pure function of radius in the leading order, okay? This means then that V theta will scale not as r2 minus 1/2, but as r2 minus 3/2. This then,
Sorry, but is it VR?
sorry, will scale is r to the power 3/2. Sorry, hold on. R next leading order, r 3/2, yes.
I don't understand why the radial velocity is proportional to the...
No, r 1/2. Sorry, Massimo. Right? The leading order velocity is r2 minus 1/2. This is radial velocity. You would think that theta velocity will be also r2 minus 1/2, but this is forbidden by the continuity equation. As a result, B theta is 1 order of magnitude larger. It is r to the power 1/2. Once it is r to the power 1, I will get back to you. This term becomes r, and this is, so I can keep the right-hand side to 2 orders. Remember when I was doing Bondi analysis, both terms were important to me. So I can keep both of these terms, and yet I can drop this stupid guy, because near the origin, it is 3rd order, right? 1, 2, this is 3rd order, I can drop it. So this, again, if you want mathematics, take a paper, this really allows me to repeat Bondi, even though one last little trick here. So this allows me to drop this term, but still here, I'm still theta dependent. However, you know this theorem in mathematics. If you have a function which starts from 0 and ends at 1, then at some point its derivative should be equal to 1, at least at one point, right? Because if everywhere derivative is greater than 1, bad, less than 1. So whatever r is at some theta, I will have this term equal to exactly m dot over 4 pi. Because if it is everywhere less than 4 pi, then I integrate over all omegas, I get less than m dot. If it is, boom, so I can replace this theta-dependent thing by m dot. Then I'm Bondi, together with Bondi's rate, okay? This is this mathematics. Let's talk physics.
Meaning,
Andrei, before you talk physics, can you point out where it wouldn't work for gamma different from 5/3?
Because,
No reason.
oh yeah, because he's right. It is this little trick, right? Here, you see, I have this critical radius. It can be shown actually that at this radius, the velocity of the flow is exactly sonic. I have this Rg equals to +0, and so my critical point is at 0. If I take a different gamma, this will go like this. My critical point will no longer be at Rg at 0, and my little trick of throwing away the theta will fail. So it is only for gamma equals to 5/3 that the rate of mass accretion does not depend on the wind velocity.
And then the follow-up is this v goes as r to the -1/2 is the free fall. But here, you're not quite in free fall all the way to r equals 0.
We will get back to it.
Right?
You will get back to it, right? I'm not, right? In fact, I'm not in free fall
ever.
ever
So
after
then
the
it's
Bondi
zero.
radius. I'm always in the, but this brings us back to Mr. Schwartzman and to really interesting physics. So this was beautiful math. Let's talk physics.
So you told us you checked Bondi on the computer. Did you check this on the computer?
Oh yeah. Because actually, because this flow happens to be potential, I formulated in this paper again. I formulated the variational principle for calculating psi. You understand, if you have a potential flow, almost certainly you have a variational principle for. If you have a variational principle, then even I can compute it on a computer, right? Because variational principle is very robust, of course, right? I took some logarithmic grid, computed, so yeah. See, it does become very spherical. Okay. So we have 20 minutes to talk interesting things.
I don't understand something trivial. You replace m dot with the derivative of m with respect to omega. But if m is independent, if you have spherical symmetry, isn't that 0?
No, it's not 0, right? Because I'm using physicist's definition. It's
the contribution per
the
solid
contribution of angle omega to the total rate of mass accretion.
the thing which you multiply by 4 pi.
Exactly.
That's astronomer's notation.
Okay, let's talk Schwartzman. So why Bondi doesn't work? Let's assume Bondi does work. Everything falls, and I will now talk Bondi without any wind. So you just move in. Since your m dot is 4 pi r squared rho v, and since your v scales as r to -1/2, back to Yasin. Assume that pressure doesn't matter too much. Then I am free falling and my velocity will scale as r to -1/2. If my velocity scales as r to -1/2 and my m dot is constant, I have no choice but to scale my density as r to -3/2. Therefore, since p scales as rho to the power 5/3, it scales as r to -5/2. And since temperature scales as p over rho, it scales as r to -1, which is the same as v squared. This is very significant. It says that for gamma equals to 5/3, my pressure will be competing with my free fall, with gravity. but as the Bondi solution is showing, will never overwhelm it. So we are in this really, who speaks English here? Precarious or precautious? So we are really in this situation where pressure is about to stop my accretion flow, but does not quite do it. Okay? This should put a flag, right? Why do I say it should put a flag? Because this temperature is due to my adiabaticity assumption, right? Because this thing is equivalent to saying that my entropy is constant, right? Because my entropy, well, in astrophysics, they call P over rho to the power gamma entropy, even though this is crazy. Okay, so my entropy is constant, right? And at constant entropy, my temperature almost stops the accretion flow. But in any real life, entropy will be growing, right? Let's be realists. Okay? So any growth of entropy will then, to make entropy larger, you will have to increase temperature beyond this thing. Then my temperature will actually stop my accretion flow. And so Schwartzman, without thinking about this particular argument, which I think is actually very powerful, right? So if your gamma is really close to 5/3, then you're almost certainly not Bondi. Anything, some trace amount of turbulence, some magnetic field, almost anything which leads to entropy growth will also shut down the accretion.
And there'll be a shock, right?
God knows what there will be. In fact,
Or
my
accretion.
old friend and co-author Quarterite kept computing what happens there up until now. And recently, for example, they computed accretion onto Sagittarius A star using like 50 Wolf-Rayet stars, actual Wolf-Rayet stars, with actual wind velocities in pure hydro. But yet the amount of turbulence was such that it also, and then of course you see that your entire accretion flow is not some nice Bondi. I looked for you, wanted to show you this beautiful picture. They have multiple shocks. So you have this like a Bondi flow, but it's like a square grid or something of all these shocks which propagate all the way, keeping like shock produces entropy. So any entropy production immediately shuts you down. So, but let me show you this beautiful Schwartzman argument. So he said, so he did not talk about this. He said something very simple. He said, okay, let's buy Bondi, but let's assume, in agreement with all astrophysical observations, that there is a little bit of a magnetic field frozen into here. What will be the fate? And here I will assume that magnetic energy is much smaller than pressure, or if you wish, thermal energy density. So my plasma easily confines this magnetic field, okay? It can support this magnetic field. Magnetic field is weak. If magnetic field is weak, it will go in just as if without any influence on the flow, okay? The magnetic field is frozen into this plasma, so as it goes, and of course, if you have this spherical flow, you experience a lot of spaghettization, right? To use Hawking's terminology, spaghettization, spaghetti, right? Because you get stretched along the radial direction, right? Just by the tidal gravitational force. So what used to be a little torus will become this really stretched thing as it goes in. But if you take like a rubber band and you stretch it like so, you put a lot of tension, obviously. Here, the amount of tension can be computed by flux conservation. The R component of the magnetic field times the cross section should stay constant because this is magnetic flux. The reason, of course, you cannot change magnetic flux is whatever. Remember electrodynamics, the rate of change of magnetic flux is electromotive force. In a perfectly conducting plasma, there will be no electromotive force. So Br R squared constant. Magnetic energy density scales as R to minus 4, which is much larger than R to minus 5 which is thermal energy density. So, says Schwartzman, case closed. If our real plasmas do contain magnetic fields, God knows what will happen. There will be some reconnection effects, there will be whatever. The reconnection effects, like you will have to destroy this magnetic field. Destroying it means producing entropy. You will not destroy it all the way to zero. You will perhaps destroy it back to thermal energy density. But then further going in, we'll stretch it again, some further reconnection event. So, says Schwartzman in that paper, we cannot really have constant entropy flow, and he predicted that actually quasi-spherically accreting, as far as I know, his was the first prediction that Bondi doesn't really work. And so, since that time, many calculations which even pretend to be first principle, be it hydro, magnetohydro, but something realistic, they all show that indeed we are non-Bondi. Again, on the other hand, if we take these primordial black holes of Yassin and really nice plasma, very uniform, without any magnetic fields, then perhaps this constant entropy can last long enough to ensure to make Bondi applicable. In the very early universe, right?
What's just remind us, what is the observation at Sag star when people do try to estimate the density of the medium and
Yeah.
do they get
It is very strongly non-Bondi.
meaning it's way below Bondi, it appears to be.
It is way below Bondi, right? The most powerful thing is due to Quartert and myself in that order, actually. I had to insist that he puts my name behind his, because it was his idea, really. Very beautiful one. He said, even before it was measured, Quartert said the following. Let us look, because the Sagittarius A star and also the same M87, they really emit in the radio, right? That's why this VLBI, right? So they emit at like millimeter, sub-millimeter wavelengths. Since this is synchrotron emission, almost certainly it will be polarized. However, they did not see any polarization at low enough frequency. Why? Because if the plasma is Bondi, now what does it mean? Think about it. That's a good question. What does it mean to have non-Bondi? Now, this guy will be atom minus 1/2. There is no arguing with that, right? If there is this free fall. To have non-Bondi, then you will have to have density which does not increase as fast as R to minus 3/2 with radius. In fact, today in numerical simulations, they find R to minus 1. This scaling, right? Almost certainly due to this entropy growth over here. So, which means, on the other hand, at Bondi radius, the density is whatever it is, right? Whatever is created by these Wolf-Rayet stars. So in these non-Bondi things, the most powerful prediction is that the density near the black hole will be much smaller, which will result in much smaller luminosity. But God knows, maybe it is radiatively inefficient how we compute luminosity. However, says Quartert, smaller density also means inevitably much smaller amount of Faraday rotation. And Faraday rotation depolarizes, right? How come they did not see any polarization at small wavelengths? That's because the amount of Faraday rotation at this very high density totally depolarized the emission. At smaller density, however, emission will be less depolarized, since Faraday is a strong function of frequency. Quartert and myself made this prediction that at high frequencies you will see polarization, which came out to be true. There are many different lines of argument.
Now they from that, in principle, you can infer how the density changes.
Yeah. There are very.
You have to make
there are claims now that it's undoubtedly non-Bondi.
So the EHT result.
The EHT will be a strong thing here, but already there are so much data that it's
fine. Still,
okay. So let me make the last. So Yassin, I already gave full credit. Now let's the last point. Why do I claim we will never know what actually happens there. Like, for example, when they will release this AEHT, they almost certainly will also do things they did for M87. They will compare it to some results of numerical simulations. Now, I want to show that these numerical simulations should be taken with about the same, how to say it, skepticism as just applying pure Bondi. I claim nobody really knows how to compute radiation of things like Sagittarius A star or M87. And my claim is based on this very simple thing, is that plasma here is a Vlasov rather than an MHD plasma. Vlasov here means that collisions between particles are totally unimportant. Vlasov was the guy who had this brilliant idea to use Boltzmann simultaneously with Maxwell. And this is called, so Vlasov simply means collisionless Boltzmann plus Maxwell. Collisionless simply means, right, a real Boltzmann equation. Boltzmann proved his H theory, whatever, right, with collisions between particles. But in some regimes, collisions happen to be unimportant. I claim that for things like Sagittarius A star or M87, collisions are obviously unimportant. Here is the proof. Consider proton, electron, they pass by each other at some impact parameter B. To have large scattering, electrostatic energy should be over the thermal energy of a particle, right? Giving me the characteristic impact parameter, or if you wish, some scattering amplitude, whatever. A characteristic impact parameter is squared over T. Let me plug the classical electron radius into this calculation, then it will be mc squared over TRE. Now, this is MeV. What is temperature near the event horizon of the black hole? Perhaps it is set by protons, perhaps not all the way to 1 GeV, but let's say 100 MeV. So this will be 10 to minus 2 times 3 times 10 to minus 13 centimeters, which is the classical electron radius. So my Coulomb cross section near the black hole becomes of order 10 to minus 29 centimeters squared, which is, I think, small even by particle physics standards, right? So what will be the density near Sag star? Even if I use Bondi, for example, the density will be what? Do I have time for this? Yes, I do. What will be the density? The ratio of the densities is Rg over R Bondi to the power minus 3/2, assuming Bondi. Rg, remember, is Gm over C squared, and R Bondi is Gm over Cs squared. So this will be therefore C over Cs to the power 3. C is the speed of light, 300,000 kilometers per second. Cs for Wolf-Rayet stars, it's 1,000 kilometers per second. So this will be 300 cubed. This will be 30 times 10 to 6.
So, Andrei, I've lost the notation n over n0. What is n0?
N0 is the density at infinity,
Oh,
whatever these Wolf-Rayet stars are giving.
okay.
Then the density grows as R to 3/2. It can grow all the way from Bondi to Schwartzman, right? And then you get something like 3 times 10 to 7 per cubic centimeter if this was 1 per cubic centimeter. I'm just throwing in numbers because it doesn't really matter. Nobody will save you from this infinitesimal cross section. So, boom, the mean free path then is 1 over n sigma 10 to 29 over 3 times 10 to 7. This is 1 kiloparsec. this is no way, right? If you have a kiloparsec mean free path and the Schwarzschild radius of Sagittarius A star, for example, is 10 to 12 centimeters. So, but in what sense do those people have a right to describe it by hydrodynamics?
But then it also can't be isothermal, right? Doesn't that mean that it will be done? Well,
So first of all,
you just have charges
back when we had Eisenstein next to our door and I was just learning astrophysics, I was using him as an encyclopedia. So I ran into his office and I said, look, you people are totally nuts. I, a plasma physicist, are telling you this is a collisionless plasma.
Yeah,
How
right.
can you describe it by hydro?
Yeah.
He said, however, there are magnetic fields. And if you have magnetic fields, the Lama radius will be very, very small, in fact.
Yeah.
So there is part of it, part of this argument is there. However,
Fine. But it's
magnetic
going
fi-
through the Maxwell's equation.
no, but the point is different. You see, however, magnetic fields have tension. Because of that, they want to become straight. So your magnetic field, in fact, is always dominated by the large scale component of the magnetic field. So perpendicular to the magnetic field, true, you are almost hydro because your Lama radius is very small. But along the magnetic field, your particle will run, if, for example, there is a magnetic field which goes around, let's say, Sagittarius A star, the particle will run millions of times around the black hole because it collides only once. So nobody really knows, as far as I'm concerned, this is the major, perhaps unsolved problem in high energy astrophysics. In what sense collisionless plasma is describable by magnetohydrodynamic equations? So, like in 2 weeks or whatever, when they make this announcement about the Event Horizon Telescope, they will tell us we have modeled it, it all works, the spin of the black hole is 35%. Maybe. Okay, that's it.
More questions?
Andrei has some questions.
Yeah.
Where does the pi come from?
Yeah, you did. I thought you were going to derive pi for us. I'm still disappointed.
Because no, that's fine. Because you see, we have this v squared here in this Bernoulli equation. This v squared can be written in terms of m dot, starting from area rho v squared. So really, I have this m over 4 pi squared, blah blah blah. So when I'm minimizing the left-hand side with respect to m over 4 pi squared, the answer happens to be 1 over 16.
Okay, so then it's the random pi followed
Right.
around.
So this pi just stays behind.
That's ridiculous. So we can estimate pi by observing pure Bondi on your neck.
No, because I do spherical symmetrical calculation, so I include pi. If you do 3D calculation in Cartesian
I see,
grid,
then you could.
this
yeah.
will be a really perverse way of measuring.
I'm wondering if you use dark matter as your gas, would the story be very different or much?
Say again?
If you use your dark matter, imagine just.
Oh, dark matter.
Yeah.
In this context, like for example, let's talk about Sagittarius A star, right? If dark matter is something like collisionless dark matter, then the actual rate of accretion is ridiculously small, right? As you know, close to the galactic center, we are actually dominated by the baryonic spike rather than the dark matter spike, right? Because there are all these stars, whatever, right? There is no influence, right? There is the central star cluster on the background of which the mass density of collisionless dark matter is thought to be absolutely tiny.
I see. So you expect this is just irrelevant.
Right, so people calculate, of course, for fun mostly, as far as I can judge, the rate of accretion of collisionless dark matter. Right, it's really ballistic mostly, so there is not much of a calculation here.
But in the very early universe, it is possible, right, that the dark matter might behave like a thermal fluid.
No, I don't think it ever behaves as a fluid, right? It remains unless you put in some collisions, whatever.
Cross-section.
Yeah. If you put some cross section, then of course the situation is different, right? But I don't know. Yasin should know more about. Do
Yeah.
people ever do this?
Yeah,
Like-
so even without accreting dark matter, it still forms some bound bound
Bound
clouds.
objects.
So it's
Right.
not gonna be m dots technically, it's not gonna.
No,
fall
but
into the black
Hogg is saying, suppose like in the early universe,
You could have
if you
accretion.
include collisions,
Yeah.
your dark matter itself becomes a fluid, then it accretes on primordial black holes. I don't know.
I'm wondering.
Since
if
primordial
Bondi
black
will
holes
work.
don't exist, we don't really know. I
I
mean,
don't know, that's the problem.
I'm just wondering if Bondi will work, and if this is a much simpler story for dark matter.
if it becomes a fluid, Bondi by definition works for a fluid. So if your regime is such that your dark matter
Is a fluid.
is authentically described by T mu nu of a fluid, then you are fine. Yeah.
Just a comment, you had this argument that there has to be a unique solution because if you put it on a computer, the point is that it's of course true, but the numerical solution could be extremely sensitive to the conditions at infinity, and you, by infinitesimal change of conditions, you could get a completely different solution in principle.
In principle, yes, but I don't think this is true in practice, right? Because mostly because of this argument, right? I mean, we can talk computers separately, but there is no beating of this argument that at R Bondi you start going in, right? Unless there is some conspiracy in your fluid, there is no really, right? Because on the other hand, I myself said that for 5/3 you are exactly on the margin. So in fact, maybe for 5/3, right, these subtleties in what happens to entropy depend on the bound. As far as I can judge, nobody, how to say it? Like for example, it is true, for example, the following thing is true, but this is not quite what you are talking about, but somewhat similar. We know, of course, that there are always viscosities. Like for example, if I into this equation, I add some kinematic viscosity. This will lead to entropy production. And as I have argued, I don't have any room for entropy production. So even a tiny friction here leading to entropy production will shut down my accretion flow. So maybe your boundary conditions can do some such thing too, but I did not find any of that.
Just a side comment.
It's fun. No, go ahead.
For like stellar black holes or neutron stars, then you would have like accreting supersonically, right? Then how does that?
For Bondi, actually, let's not go to relativity actually, because your question already makes sense for a non-relativistic accretion. If I take a point Newtonian mass, consider spherical flow, then it so happens, which actually explains the success of my little theorem. For gamma equals to 5/3, the sonic surface, the surface where the velocity becomes equal to the local speed of sound, okay, happens to be on top of the accretor. And because of that, I was able to do everything. If gamma is less than 5/3, then in fact, the sonic surface moves away from the accretor. At the sonic surface, you smoothly cross from subsonic to supersonic flow. And once you are in a supersonic flow, of course, nothing will matter, right? You will just go supersonically into the black hole. So the answer is you always go supersonically because in fact, you always have gamma less than 5/3 close to the black hole, right? Because close to the black hole, you become hot enough for relativistic effects to show up, and you move from 5/3 closer to 4/3. However, none of this matters unless for Yassin, because actual flows are so strongly non-Bondi, so strongly turbulent, that who cares? Subsonic, supersonic.
Yeah, like at infinity, it's already flowing at supersonic speed. So if you were like in local, like
at infinity, oh, you are saying if V is greater than CS. I misunderstood you perhaps. Well, I totally misunderstood you. Let me answer this because this is beautiful. I will take 2 minutes, but probably people should go, right? It's already 7 minutes. Okay, so anyway, so this is a beautiful thing where saltpeter.
No one here is a prisoner. We didn't lock the doors.
Oh, America is a free country. Still, I thought it changed. Okay, so anyway.
Just put your mask back on.
So V less than CS, is this what you're asking, right?
Yeah.
Right, this is why it is important. It's actually very interesting. This is where great Salpeter made a crazy, terrible mistake. Salpeter is some astrophysicist. So, and also a physicist. So suppose you have this mass M, and suppose, in fact, CS is 0 at infinity, so you have cold flow. If it is cold, then it is just like this dark matter you have been asking about. It is collisionless, it's just particles.
It's like
No?
sailing a boat.
Whatever, it's just particles, right? Boom, this goes straight in, this gets deflected, goes this way, this gets deflected, goes this should be online, obviously. They intersect over here. Now I recall that I have a fluid rather than collisionless particles. Then when they collide here, what will happen? Imagine they actually, like in Zeldovich, they stick together. Imagine this is inelastic collision. These are just sticky particles. If they stick together, and if they were at 90 degrees, then you will get a particle at rest, which will be sucked into the black hole. And so Salpeter thought that cold wind accretion looks like this. There is a shock behind the black hole, and along this shock, things move in from the back end, so to speak.
And we learned that in grad school, and we learned it would slow down the black hole.
Right, and there's dynamical friction. This is all, of course, not right. In reality, you get a bow shock, and then there is these things, whatever, right? So then, of course, indeed, you get a bow shock, supersonic flow over here, so the whole thing changes. This, however, happens only if V is greater than CS. Yeah. If CS is greater than V, the flow remains nice and smooth all the way to the black hole with the sonic surface on top of the black hole. Okay, we should stop, I think.
Yeah, let's move the discussion to coffee. Let's thank Andrei again, and thanks. Thanks for agreeing on such short notice.
Coffee and cookies?
Yeah, there should be coffee and cookies.